This training is for MOC 2404-762, the A1-103J High-Case Sour Oil Traps Technology Upgrade. Let's start with an overview so we are all on the same page with exactly what equipment we are talking about. Here is an overhead shot of Ammonia Plant 1. The stripper tower is here on the left. The cooling tower is here on the right. The top of the shot is going north. As we zoom in, you will start to see the 103J syngas compressor come into focus. With this view, you can easily see the four main sections of the 103J compressor train: the high case, the low case, the topping turbine, and the condensing turbine. This training is going to focus on the seal oil system on the high case, specifically around the oil and syngas mixture after it leaves the compressor seal cavities, which we call sour oil. This sour oil travels through a piping system under the compressor deck and into a skid containing the sour oil traps. Here's what the high-case sour oil traps and skid look like in the field. The piping for the high-case sour oil traps is congested and can be challenging to properly trace out. Let's look at some simple drawings while we discuss the flow through this sour oil system. Inside some of the seal oil cavities engineered into the 103J high case, seal oil comes into contact with a small amount of syngas from inside the compressor case. This is a designed aspect of how the seal oil system works to contain the high process pressure and hazardous gases inside the case from escaping to the outside of the system. These special cavities have inlet and outlet piping to allow a continuous flow of clean seal oil to enter and a path for the mixture of seal oil and gases, which we call sour oil, to exit the seal area of the machine. This sour oil travels down the piping system and into the sour oil trap. This small knockout pot is a vessel that allows for the separation of gases from liquids. The liquid, oil in this case, falls to the bottom of the sour oil trap, while the gases separate from the liquid and get pushed to the top of the vessel. The gas leaving the high-case sour oil trap is piped directly into the first stage suction piping, effectively recycling this small amount of syngas that leaked down the shaft through the seals back to the process side suction of the machine. The oil collecting in the bottom of the sour oil trap flows out the bottom of the vessel through piping to the degasifier tank. This tank, which has a 50-pound steam coil underneath it, is used to heat the sour oil up to help separate any further small amounts of gas and to evaporate any entrained liquids in the oil. In our system, this would usually be trace amounts of water and ammonia. The oil, no longer sour, then flows back into the large oil tank reservoir for reuse. Now that we understand the basic sour oil flow from the high case, let's look at this system in more detail. There are actually two separate seals on the high case of 103J, one on the inboard and one on the outboard side of the compressor case. Each of these seals has its own sour oil piping leaving the machine and running down to a separate sour oil trap for each side. After separation of the oil and gas occurs, the gas that leaves the top of each sour oil trap joins together in a common header, and this one line flows back to the first stage suction of the compressor. This line is big enough so that both high-case sour oil traps can be in service at the same time and share this line. On the bottom end of each sour oil trap, the piping that lets the oil flow towards the degassing tank also joins together into one pipe or header. This shared piping is designed to be large enough so that both high-case sour oil traps can be in service and share this line at the same time. As a reminder, at this point, this is an oversimplified version of the system, and we will continue to add details as we develop our understanding of the flows. In this shot, we have added some control equipment to the system to help us manipulate variables like flow, pressure, and levels in and around the sour oil traps. Let's start by looking at the liquid level in the sour oil trap and how we control that. First of all, let's think about why we need to control the liquid level in the trap. What would happen to the oil level if the level control valve and block valve were left wide open? To answer that question, we need to know some information about the system. Let's start with pressure. How much pressure is on the degassing tank? If you remember, it has a vent to the atmosphere, so we will say it has no pressure on it compared to the rest of the system. Now let's think about the pressure inside the sour oil trap itself. How much pressure is on it? To figure this out, let's look at the top of the trap, where the gas exits. Where does the gas go when it leaves the top of the trap? Back to the first stage suction process side of the 103J compressor. How much pressure does this suction line have on it? On the day this training was made, the Ammonia 1 plant was running 340 pounds of suction pressure. This pressure can and will fluctuate based on several factors throughout the plant, but this is a normal operating pressure based on historical data for the last several years. As we discussed before, the flow of this gas is from the top of the seal oil trap and towards the suction piping. When the gas leaves the top of the sour oil trap, it flows into a restrictor plate, also called a flow orifice. This mechanism, a solid plate with a small hole in it, is specifically engineered to only allow so much flow through it at a time. I know you thought we were talking about pressure. In this part of the system, gas flow and gas pressure are very closely related. To help understand what this orifice plate does, let's think about what would happen if it wasn't there. If the gas was allowed to flow as quickly, or as much, as it could, through the sour oil trap, and into the first stage suction piping, the gas would be moving so quickly through the trap that it would carry most of the liquid oil out the top with it. That is not what we want to happen. We are trying to get a good separation of the gas and the liquid inside the sour oil trap. This restriction or orifice plate slows the gas flow down, only letting a set amount through the small hole. As the gas flow, traffic jams, into this plate, it slows the flow down, which raises the pressure upstream of the plate. We usually use the term back pressure for this scenario. So, the pressure inside the sour oil trap is going to be slightly higher than the first stage suction piping. For this specific scenario, let's assume the sour oil pot is 5 psi higher than the suction piping. Now that we know how much pressure is on the inside of the sour oil trap and how much pressure is on the degassing tank, it is easy to answer the earlier question about what would happen if the valves were left wide open on the bottom of the sour oil trap. The pressure inside the trap would quickly push all the liquid out the bottom, and the trap would go empty. We would also lose our ability to separate the liquid and gas in the trap because all the gas and liquid would want to flow out the bottom of the trap, taking the path of least resistance. In this scenario, we would also be letting gas from the suction line flow backwards into the top of the trap, out the bottom, and into the degassing tank, which would result in syngas going out to the atmosphere from the vent on degassing tank. With the level controller in place and working, we can regulate how much oil we let out of the bottom of the trap, which will in turn manage the level in the trap itself. As we just learned, keeping an appropriate oil level in the trap is critical to the system working correctly. How do we know what the level of oil is inside the sour oil trap? The answer to that is changing, which is what this MOC is about. The way the level is currently identified is with an internal float mechanism, which is not the most reliable technology to use for this application and is difficult to work on. Maintenance requires removal of the top of the sour oil trap. We are updating this level element to a guided wave radar style, which is better technology for this application.
The transmitter measures the time it takes for the transmitted signal to travel down the probe, reflect off the material surface, and return to the transmitter.
This new level element will be installed in a separate column, not inside the seal oil trap, so it will be easier to maintenance. To accomplish this change, we are going to remove the local site glass column. We will also demo the physical pieces at the top of the seal oil trap. These are part of the old float level indication, and a spool piece will be installed here on both high-case seal oil traps. Replacing the old site glass will be this new dual column setup, with the level transmitter and a local Magtech style indication. The Vega MAG series magnetic level gauges are designed as an indirect reading liquid level indicator. The magnetic level is constructed of a non-magnetic chamber, an externally mounted flag indicator chamber, and magnets housed within a float. The MLI magnetic level indicator gauge chamber contains a magnetic float and is completely isolated from the indicator housing attached to the outside of the gauge chamber. External indicators, or flags, represent the liquid level. The magnetic float maintains a magnetic bond with the external level flags. As the level of the process medium fluctuates within the sour oil trap and gauge chamber, the float reacts accordingly, with the flags visually correlating to the level of the fluid within the chamber.
A float designed for the specific gravity of the process liquid travels inside the MLI chamber, tracking the rise and fall of the media. This float contains an internal magnetic assembly that couples with the external visual indicator. The individual flags, or flippers, rotate 180 degrees as the level rises and falls, indicating the position of the liquid inside the MLI, and therefore indicating the level of the liquid in the vessel.
When complete, our new setup will look like this, with isolation valves on the top and bottom leg, coming off the sour oil traps. Then the guided wave radar column, and then the Magtech local level gauge, with a top bleed and a bottom bleed. Let's discuss the recommended way to put these columns in service. When the gauge is mounted and ready to be placed in service, partially open the top process connection valve first. This valve must be opened slowly to allow initial pressure and temperature equalization between the vessel and the level gauge. Opening the valve in this manner allows the process conditions of the vessel to equalize with the gauge slowly and reach operating conditions at a slow, even, and reasonable rate.
Caution!
Do not open the bottom process connection valve first. If you open the bottom valve first, with the top valve closed and the vessel under pressure, the internal float rises instantly. If the float rises instantly, it will lodge itself into the top of the chamber and cause severe damage to the float and the chamber.
Hey, we've got a problem here.
What did you do?
Nothing, I stirred the tanks.
Whoa, hey.
This is Houston. Say again, please.
Houston, we have a problem.
When the gauge chamber has obtained normal operating conditions, open the bottom process valve connection slowly. Opening the bottom process slowly allows proper fluid entry into the gauge chamber under normal operating conditions. The level indicator should rise vertically, thus rendering a fluid level. Flag or flipper indication will result in black to yellow rotation of the flippers as the fluid rises. At this point, installation should be complete. Now, let's talk about how to take this new level indication and Magtech columns out of service correctly. Close the bottom isolation valve first, and the top valve second. Open the vent valve slowly, to depressurize the gauge, especially if the gauge has been under pressure. Open the drain valve slowly, or remove the drain plug carefully, to allow any remaining fluid to drain from the chamber. The other aspect of this MOC is to change the actuators out on the level control valves LV206 and LV207. Currently, these actuators are an old pneumatic-style controller that does not have the capability to communicate any information, like the level, valve loading, or set point into the DCS. These actuators will be removed and an upgraded digital actuator called a DVC will take its place. The valve bodies and internals will stay as they are. The new guided wave radar level transmitter and digital controllers will allow this control loop to be ran from the DCS. On the DCS, the graphics for the sour oil trap level controls will look like this. The faceplate for the actual level control valves will look like this. Let's go over how the controls will work to maintain the level of oil in the sour oil trap. They are set up a little different from the normal level control scheme. There are several alarm points set up on the logic for these controllers. There is a low alarm set at 30%. So if the oil level falls to 30%, the DCS will sound an audible alarm and a message will appear in the alarm banner to alert the console operator to a problem. The alarm message will read what is on the faceplate of the controller and read which alarm it is, in this case low. Next there is a low alarm set at 45% level. This alarm will not send an audible or message to the console operator. This alarm set point will be used to tell the control valve LV206 or LV207 to go closed, all the way closed to 0%. On the top end, there is a high-level alarm at 65%, which will not give the operator a notification or message. This alarm set point will be used to tell the level control valve to come open to 10%. One move from closed to 10% open, and then stay at 10% open until the level gets to 45%. The low-level alarm set point, at which time, the low-level alarm will tell the valve to go shut all the way. the valve will remain closed completely until the level, hopefully nice and slowly, drifts back up to 65%. If for some reason, this system was unable to move the level out of the sour oil trap, at 70%, the console operator would receive the high level alarm, which would alert with an audible alarm sound, and a message on the alarm banner. This would indicate that there is a problem with the system, the oil level is too high, which should initiate some troubleshooting by the operations team. You may have noticed, the controller is in the manual mode. That is the only mode available for this controller. LV206 and LV207 cannot be placed in auto, or cascade, those modes are not available. Also, the console operator cannot change the valve loading, even though the mode says manual. These valves LV206 and LV207 are not truly in manual operation. If there is an issue maintaining this level, manipulation of either of these valves will require the assistance of the controls group. For review, the changes being made to the A1103J high-case sour oil trap system are the old sight glasses will be removed and replaced by dual-column guided wave radar level transmitters and local MagTech level gauges. There will be a new spool piece added to the top of both the sour oil traps to replace the old level element pieces that are being removed. The actuators and positioners on both LV206 and LV207 will be replaced with new upgraded digital style equipment. The system and its data will now be ran into and from the DCS system, where before it was all local control. There is new logic to how the level controllers will operate in an abnormal manual mode that cannot be manipulated by the console operators.